All right, let's find some higher order derivatives. Let's take the second derivative of this function. So I'll start with the first derivative. So I've got f prime of x is equal to, and this is a chain rule problem. I've got a function inside a function. So I'll do that outer function first. I'm going to multiply that 4 over to the 5. So I've got 20, and then my blur, my inside function, and subtract 1 from the exponent. And then I'll go back and take the derivative of the inside, which is just -7. And then I'll clean that up. I've got -140 times 2 minus 7x to the third. First derivative is done. And so now I just act like this is the new function and I take the derivative again. And that's going to get me that second derivative. So f double prime of x is equal to, and then again it's a chain rule. I've got my inside function, my outside function. So I'll multiply that 3 over. Oh, -140 times 3 is -420. Somebody tell me if that's wrong. And then my inside, and then subtract 1 from the exponent. Go back and take the derivative of the inside. Oh, I was not prepared for this. What is 420 times 7? 0, 14. I should have written this out before. 2,940? Oh, that's fine. Negative times a negative. If that's wrong, just roll with me. And 2 minus 7x squared. Piece of cake. And we could do that as many times as we wanted. We could find f triple prime of x. We could find f to the sixth of x, right? We could find the sixth derivative of f of x if we wanted to. But we will stop there since it just asked for the second derivative. Let's do another one. Let's find the third derivative of f of x equals x cubed plus 3 over x cubed. I already don't like that. I want to rewrite that before I even start. I want to make that x cubed plus 3 x to the -3. I could do a quotient rule here, but there's just no sense when you can just rewrite the exponent and take care of that problem. So let's get cracking here. I can change this to y if I want to. Y prime, first derivative, is 3x squared minus 9x to the -4. And if I were stopping there, I'd take that exponent and I'd move it down to the denominator, but I'm going to take another derivative, so I might as well leave it there. The second derivative, y double prime, is equal to 6x plus 36x to the -5. And again, y triple prime, or the third derivative, is 6 plus, oh, I should have done my arithmetic before I started recording. I got my scratch paper here. What's 36 times 5 is 30, 180, -180. X to the -6th. And since this is my final answer, I will go ahead and write that properly. So that'll be 6 minus 180 over x to the 6th. These aren't too bad, right? You're just doing the same problem over and over again. That's all a higher order derivative is. They get a lot more interesting when we start doing implicit differentiation. Let's look at this beast. We want to evaluate second derivative of, and right away I see I've got an xy term. That tells me I'm doing implicit differentiation here. So it wants us to find that second derivative and then evaluate it at this point. And you're going to see we're real glad that they're asking us to evaluate at a point because this is going to get gross in a hurry. So let's start by taking the first derivative. So right in here I see already I've got a product rule. I've got a first and a second with that xy. So the derivative, the first times the derivative of the second, which is just 1 times dy dx. Remember, anytime you take the derivative of a y term, you have to add on that dy dx. So I've got the first times the derivative of the second, plus the second times the derivative of the first, which is just 1. And now I can move on to the next term. Derivative of a constant is 0. Derivative of 2x is 2. And the derivative of y squared is 2y dy dx. Oh, I gotta keep the cat off the computer. Oh, this is fun. So a lot of my videos were recorded before I got a cat, but it's 2020. That's Mr. Spock meowing in the background. Where was I? Solving for dy dx. So I'm gonna gather all my dy dx terms on the same side. Dy dx minus 2y dy dx. Can you hear him yowling in the background? It's fine. And then I'll move my y term over. 2 minus y. Now, here's the part where I would factor out the dy dx. I'm going to get a little lazy with my steps there and say that dy dx is 2 minus y over x minus 2y. I know I'm going to factor those out, move them over, so I'll just leave it at that. Now, I need to find the second derivative. So I'm going to start with this. I'm going to rewrite it over here so we can see it. I had dy dx is equal to 2 minus y over x plus 2y. And we're evaluating that at the point negative 1/2, 0. So now I'm going to pretend this is the problem I'm starting with now and take the derivative again. So now I have a quotient rule. So the second derivative is low d high. So the derivative of the high here, that's just negative 1 dy dx. So I have low d high minus high d low. The derivative of the low there is 1 plus 2, but then that y means I have to do the dy dx. Closing my parentheses there, all over low squared. Oh, that got ugly in a hurry. Now, here's what you normally have to do. Here's what you normally have to do. Normally, you would take now this dy dx term and you would sub it in everywhere that you see a dy dx. Can you imagine how gross that fraction would be, right? You got fractions inside of fractions with distribution, it would be a mess, right? But this problem is better for us because we're evaluating this at a point. So what I can do is I can go ahead and evaluate dy dx at negative 1/2, 0, and then just plug that number in. I can skip this step of plugging in the algebraic expression and just plug in the number. So let's do that. If I plug in negative 1/2, 0 into, this got real messy, and I'm sorry about that. So I have 2 minus y, where y is 0, over x plus 2y, which is just 0. So I have 2 over negative 1/2, that's just negative 4. So everywhere that I see dy dx, I can just plug in negative 4. And while I'm at it, I'm going to go ahead and plug in my x terms and my y terms to the second derivative here. So the second derivative is equal to, so let's do this. Got negative 1/2 plus 2y, but that was just 0, times negative dy dx. dy dx was negative 4, so negative times a negative means I've got 4, minus 2 minus y is 0, times 1 plus 2 times negative 4. And all of that is over negative 1/2 plus 2 times 0 squared. This isn't so bad. Let's see what we've got going on here. So negative 1/2 of 4, that's going to be negative 2, plus, what did I have going on here? I've got negative 8, 1 minus 8 is negative 7, times negative 2, that's plus 14. And then in the denominator, I had negative 1/2 squared, so it's 1/4. So that is 4 times 12. Whew, 48 is our final answer. Okay, so again, I know they got pretty messy, but the moral of the story there was once you find the second derivative, you usually have to take your first derivative and plug it in anywhere that there's a dy dx. But because we were evaluating it at a point, right, that's what made this problem better. Because we were evaluating at a point, we can go ahead and get the number, the numeric value for dy dx, and then plug all three of those things in at once. Plug in your x, your y, and your dy dx, and then you can get the numerical expression, and then that monstrosity simplifies into a lovely, lovely number.